Okay, let's dive right into this explainer. Today, we're decoding the highly technical engineering disclosures that actually help investors measure real product performance in the clean energy sector. We're looking directly at the SASB standards for fuel cells and industrial batteries, and we are going to translate some seriously heavy engineering metrics into clear, actionable financial intelligence. If you've ever wondered how analysts figure out which clean energy tech is actually winning the race, you are definitely in the right place. So, here's the million-dollar question we have to ask ourselves. How do financial analysts cut through all the marketing fluff to evaluate the true operational efficiency of fuel cells and industrial batteries? Because let's be honest, companies can make all sorts of wild claims in their shiny brochures, but when it comes down to the bottom line, investors need hard, standardized data. They need a way to compare a massive stationary fuel cell against a huge array of industrial lithium-ion batteries without just comparing apples to oranges. To pull that off, analysts rely on a very specific set of parameters. Just listen to this alphabet soup for a second. Watt per kilogram, LHV, coulombic efficiency, cycles. I know, if you don't know what these mean, evaluating clean energy products is kind of like trying to read a book in the dark. But today, we're using the SASB framework to decipher these exact terms, transforming them from intimidating jargon into a really powerful analytical toolkit for understanding product performance. Here is our roadmap for today. First, decoding product efficiency. Second, measuring battery storage capacity. Third, calculating the efficiency ratios. Fourth, the 20% degradation rule. And finally, empowering the modern investor. Section 1. Decoding product efficiency. In the world of industrial batteries and fuel cells, the use phase of the product is literally everything. It's the moment these machines are actually plugged into the grid or powering heavy machinery. High product efficiency directly drives lower environmental impacts and, crucially, a significantly lower total cost of ownership. The SASB standards give us a literal dashboard mapping out 5 specific metrics, from RFC 410A1 right through to point 5, meticulously covering storage capacity, energy efficiency, and operating lifetime. This is exactly what companies must use to report their real-world performance. Section 2. Measuring battery storage capacity. Right, let's establish the baseline storage capacity for industrial batteries. The absolute gold standard here is gravimetric energy density, which you'll commonly hear referred to as specific energy. This is just the ratio of nominal energy in watt-hours to the mass of the product in kilograms, or watt-hours per kilogram. It's the ultimate weight-to-energy ratio. Think about it. If a battery is way too heavy for the amount of power it stores, it's virtually useless for a lot of industrial applications. Investors use this metric to instantly gauge how competitive a battery's baseline capacity truly is. But here is where the SASB standard gets wonderfully precise. Companies can't just throw out a single cherry-picked number for their absolute best battery prototype. No way. They must report this specific energy weighted by actual unit sales volume, and it has to be broken down by distinct applications, like portable, motive, or stationary, and by chemistry, whether that's lead-based, nickel, lithium, or sodium-based. This totally prevents companies from hiding the poor performance of their older product lines behind the flashy numbers of a brand new prototype. Section 3. Calculating the efficiency ratios. So, shifting our focus from raw storage capacity to real-time operations, we have to ask, how much of that stored energy is actually usable and how much is just lost in the conversion process? Because fuel cells and batteries operate on fundamentally different chemical principles, we can't really measure their efficiency the exact same way. Fuel cells generate power from fuel, right? So they are measured by electrical and thermal efficiency. Batteries, on the other hand, simply store and release power, so they rely on a different metric entirely, called coulombic efficiency. First up, the fuel cell math. SASB requires engineers to calculate electrical efficiency by taking the net electricity produced and dividing it by the total fuel energy input. Thermal efficiency takes the net useful power output divided by that same fuel input. But here is the real secret to keeping companies honest. The calculation must use what are known as lower heating values, or LHV. By enforcing LHV across the board, investors can be absolutely certain they're looking at precise, apples-to-apples ratios of power output versus fuel input, no matter who actually manufactured the fuel cell. Now, for batteries, we use what's called coulombic efficiency. Simply put, it's the ratio of the energy you get out of the battery during discharge divided by the energy you had to put into it during charging to restore its original capacity. In a perfect world, this would be 100%. But energy is always lost as heat, so a higher coulombic efficiency just means a superior battery that wastes less power during its charge and discharge cycles. And of course, transparency is absolutely paramount here. Just like our capacity metrics, these efficiency ratios must be strictly categorized by specific technology types. For fuel cells, that means breaking down sales-weighted efficiency by acronyms like PEM or solid oxide fuel cells. For batteries, it's split by chemistries like lead, nickel, lithium, or sodium. Standardizing the data this way means an analyst can directly compare the efficiency of Company A's lithium-ion product right alongside Company B's identical product category. Section 4, the 20% degradation rule. All right, now we're building toward a fascinating shared benchmark that applies across all these entirely different technologies. The magic number? 20%. This number officially marks the end of an operating lifetime in the eyes of the SASB standard. Whether we are talking about a massive fuel cell powering a whole hospital or a bank of industrial batteries stabilizing a solar farm, the clock basically stops the moment the equipment suffers exactly 20% degradation in its performance. But how we actually reach that 20% limit completely depends on the technology. For fuel cells, operating lifetime is calculated simply by the number of operating hours until 20% net power degradation occurs. For batteries, it's measured by the number of full charge and discharge cycles the battery can handle before hitting a 20% capacity degradation. So it's hours for fuel cells and cycles for batteries. The logic here is straightforward, but man, is it powerful. You track the hours or cycles, you wait until you hit exactly 20% degradation, and then you report that standardized number. I mean, we've all had a smartphone that suddenly dies when it says 40% battery, right? Industrial buyers want to avoid exactly that. By defining end of life so rigidly, a company cannot claim their battery lasts for 10,000 cycles if, by cycle 5,000, it barely holds a charge. The 20% rule ensures absolute honesty and real comparative value. Section 5. Empowering the modern investor. Let's pull back for a second to see the big picture. Why do Wall Street analysts care so deeply about these specific engineering variables? Well, it's because it builds a complete comparative matrix. You've got battery capacity in watt-hours per kilogram, energy efficiency using LHV, coulombic battery efficiency, and operating lifetimes measured in hours and cycles. This is exactly how you cut through the marketing noise. You just ask for the hard data that fills out those exact 5 metrics. And honestly, the stakes could not be higher. As the standard specifically notes, advances in this technology are absolutely critical for integrating renewable energy into the grid. Strong efficiency metrics don't just lower operating costs for a single factory somewhere. They represent the actual technological milestones required to reliably capture solar and wind energy, store it efficiently, and then deploy it when the sun isn't shining. The companies posting the best numbers here are the ones literally rewiring our global energy infrastructure. But that brings us to a really provocative thought to end on today. We just learned that hitting 20% degradation marks the official end of a product's operating lifetime. But mathematically speaking, that means the unit still retains 80% of its original capacity. Think about that. When a multi-ton industrial battery hits that threshold, it's retired. So what exactly happens to that remaining 80%? Does it just go to a landfill? Is it recycled? That massive logistical challenge brings us into the incredibly complex world of product end-of-life management, a fascinating topic that for sure deserves an entire explainer of its own. Until next time, keep analyzing, and thanks so much for joining us.